So welcome you back to this problem solving session. So in the last problem solving session, we solved some of the problems of assignment number 4. We'll continue to solve some more problems of assignment number 4 so that you can get a feel of the topics covered under Bayes and minimax estimation. So we did the first 4 problems. So let us try to do the 5th problem. Of assignment number 4. So for j is equal to 1 to p, it says delta I is a Bayes estimator of theta I under the square lateral loss function. C1, C2, Cp is constant, then my claim is summation j is equal to 1 to p Cj delta j is Bayes estimator of summation j is equal to 1 to p Cj theta j. So the proof is very simple. So Bayes estimator summation j is equal to 1 to p Cj theta j is the posterior mean. So posterior means expected value of S given x of summation j is equal to 1 to p Cj Sj. Right, where S is a vector S1, S2, Sk. Right? Because Bayes estimator is nothing but the posterior mean. And what is this? This is same as summation j is equal to 1 to p Cj expected value of S given x of Sj. But what is this? This is nothing but a posterior mean of Sj. And Sj corresponds to the theta j. So this is same as posterior mean of theta j, which is nothing but the Bayes estimator of theta j. And Bayes estimator of theta j is given to be delta j. And that proves the result. Simple. Because in the square lateral loss function, you know that the unique Bayes estimator is nothing but the posterior mean. So the unique Bayes estimator of summation Cj theta j would be the posterior mean of Cj theta j. But theta j is represented by a random variable Sj, so it would be the posterior mean of Cj Sj. And this vector S is S1, S2, Sp. By the linear property of expectation, I can take the expectation inside. It becomes summation j is equal to 1 to p Cj expected value of S given x of Sj. But this is nothing but posterior mean of theta j. And posterior mean of theta j under square lateral loss function is nothing but a Bayes estimator of theta j, which is nothing but delta j. And that is what it proves. So it proves that if delta j's are Bayes estimator of theta j's and Cj's are constants, then summation Cj delta j is a Bayes estimator of summation Cj theta j. Okay, now let me do another problem. A part of this problem I have already done in one of those video lectures. So let us try to see what does it say. So what you have is x1, x2, xn, IID, normal theta, sigma naught square. Sigma naught square is known to you. This is unknown. Sigma naught greater than 0 is known. Estimate is g theta. G theta is equal to theta. Under the square lateral loss function, so my L theta is A minus theta whole square. My prior is normal mu naught and tau naught square. prior for theta. Mu naught is in R and tau naught. So first find the Bayes estimator. Delta naught x is equal to x bar cannot be Bayes. With respect to any proper prior. So this all I have done in one of those video lectures, but I can again repeat it. But it is admissible at minimax. X bar is generalized Bayes. So this part says it cannot be Bayes with respect to proper prior, but it can be a Bayes with respect to improper prior, which is a uniform prior on whole R. So X bar is generalized Bayes with respect to uniform prior, which is same as Lebesgue measure on R. So to do this, I'll not repeat each and every step. To find the Bayes estimator, first you have to find out, you know that loss function is squared error. So Bayes estimator is nothing but posterior mean. So what you need to find is just the posterior mean. For that you need to find out the posterior distribution. So what is the posterior distribution? F of s given x at the point theta given x. So it is a conditional distribution of theta given x. But conditional distribution is always proportional to the joint. So it is always proportional to the joint distribution of s and x at theta and x. But joint can be written as conditional distribution of x given s. So this would always be proportional to conditional distribution of x given s at the point x and theta, and then the PDF of s at the point theta. So that is a joint distribution of x and s. What is this? This is same as product I is equal to 1 to n, because f of x given theta is nothing but normal, that is given to you. So 1 by sigma naught root 2 pi e to power minus 1 by 2 sigma naught square summation I is equal to 1 to n xi minus theta whole square. There is no summation over here. Summation will come later on. And then fs theta, theta prior is given to be this, which is nothing but 1 by tau naught root 2 pi e to power minus 1 by 2 tau naught square theta minus mu naught whole square. You can combine everything and then you can easily check, which I did in one of those lectures. Let me just try to see if I can. So this turns out to be, if you collect every terms, it turns out to be e to power minus 1 by 2 n by sigma naught square plus 1 by tau naught square and then when you are making a perfect square, it will become theta minus nx bar by sigma naught square plus mu naught by tau naught square divided by n by sigma naught square plus 1 by tau naught square. So in fact, it is clear from here that the conditional distribution of S given x equal to x is nothing but normal, with mean as this quantity n x bar by sigma naught square plus mu naught by tau naught square by n by sigma naught square plus 1 by tau naught square And what is the variance? Variance is equal to 1 upon of this quantity. So 1 upon n by sigma naught square plus 1 upon tau naught square. Now note that we have given a very nice interpretation of this. Normally so a Bayes estimator is nothing but the posterior mean. So delta pi x, which is nothing but nx bar by sigma naught square plus mu naught by tau naught square by n by sigma naught square. Now this is a very nice interpretation. X bar is the mean of sample. Mu naught is the mean of the prior distribution. So I have a two sources of information. One is the sample x, one is the prior distribution. So what it says is, after you have taken a data, update your prior information mu naught by considering the convex combination of mean of sample and mean of the prior distribution. And what are the weights attached to the two? The corresponding variances, inverse of the corresponding variances, because variance of x bar is sigma naught square by n. What is the variance of mu naught in the prior distribution? Tau naught square. So inverse weight is 1 upon tau naught square. So this is what it is. In fact, if you want, you can write down this as n by sigma naught square divided by n by sigma naught square plus 1 by tau naught square into x bar plus 1 upon tau naught square upon n by sigma naught square mu naught, which in fact can be written as alpha times x bar plus 1 minus alpha times mu naught. This was the source of information from the data. This is kind of a mean of the prior distribution. So it says you take the convex combination of mean of the two sources of information with weights alpha and 1 minus alpha, where alpha is n upon sigma naught square. Note that sigma naught square by n was the variance of x bar. So with weights proportional to inverse of the variances. So very nice interpretation. Now I have to show that x bar cannot be Bayes. Now you know that expected value of x bar is theta. So if it is Bayes, its Bayes risk has to be 0. So if its Bayes risk turns out to be non-zero, that would show that x bar cannot be Bayes with respect to any prior distribution. So let us try to r theta x bar is nothing but expected value of x bar minus theta whole square, which is nothing but variance of x bar, which is equal to 1 upon n. So with respect to for every theta. So what will be the Bayes risk of x bar with respect to any proper prior distribution? It would be expected value of 1 by n. It does not depend on theta. So it is always 1 by n, which is not equal to 0. So x bar was unbiased. So if it had to be Bayes under a squared error loss function, r pi x bar should have been 0. So this implies that x bar cannot be Bayes with respect to any proper prior. Now note that if x bar was Bayes and if it was a unique Bayes, then x bar would have been admissible by the result which we did. Even if it was not unique Bayes, because normal belongs to exponential family, so risk function would always be continuous function of theta. So even if it was Bayes, x bar would have been admissible. But what we have shown is x bar cannot be Bayes with respect to any proper prior distribution. So then I use the second result, which says that even if x bar is a limit of Bayes in certain sense, then it would be admissible. So for that, what I need to show is if there exists a sequence of priors, so I try to show that limit m going to infinity, r pi m x bar minus r pi m delta pi m. So it is the base divided by pi m of any open set, so I can take it to be any interval a b. I try to see whether this is 0 or not. If I can show that this is 0 for a sequence of priors pi m, then x bar turns out to be admissible. So what I do is I take pi m to be, as I said, what I have realized is x bar is generalized based with respect to uniform prior. This you can see the lecture notes. Turns out to be very straightforward, because when you have a uniform prior distribution, posterior distribution would be distributions of x bar given theta only. So theta minus x bar would come. So posterior mean would be x bar. That is the whole idea. So what I do is, so it is a base with a uniform prior. Uniform prior means variance in a certain sense is going to infinity. So what I do is I consider the same prior with variance going to infinity. If variance is going to infinity, I can take mu naught to be 0 and sigma naught square to be m. So what is the delta pi m x in this case? N x bar, yeah? What should be the mu naught is 0, so n by sigma naught square is m, so n by m divided by n by m, sorry, tau naught is 1, so n by sigma naught square divided by n by sigma naught square plus 1 by m into x bar. That is what this quantity turns out to be. So what I do is I consider its base risk. So r delta, so first r delta pi m there may be some mess up with notations, doesn't matter. This is nothing but expected value with respect to joint distribution of S and X of n by sigma naught square by n by sigma naught square plus 1 by m x bar minus s whole square. Right, which is nothing but, I can write down this. You see, this would have been, normally it would have been first you take respect to x given s and then s, right? So when theta is fixed and then you integrate out theta. I can convert this whole expectation into E of x, marginal of x, into E of s given x, of whatever this quantity is. Now note that when I am taking E of s given x, this is s minus this. But this quantity is nothing but expected value of s given x, because it is a posterior mean. So that means E of s given x of this quantity is nothing but a posterior variance of s given x. But posterior variance of s given x, we had just seen, we had calculated what was the posterior variance was. So this is nothing but, because we had seen posterior distribution is normal with mean as given by that quantity. So this is nothing but E of x, posterior distribution was nothing but 1 upon n sigma naught square plus 1 upon m. Is that okay? And there is no x over here, so it becomes n by sigma naught square plus 1 by m. This is due to the fact that s given x equal to x, posterior distribution is nothing but normal with mean. That is what just now we saw that. So r pi m x bar minus r pi m delta pi m by pi m of AB is nothing but, you can see how much this turns out to be. R pi m x bar we have seen is 1 upon n minus, this would be 1 upon m, right, minus 1 upon n by sigma naught square. This should be not 1 upon n, sigma naught square by n, right? Because variance I have taken to be sigma naught square. So it is sigma naught square by n minus 1 upon n by sigma naught square plus 1 by n divided by pi m of AB. Pi m of AB is nothing but, pi m is normal 0, 1. So 1 by sigma, which is root m, root 2 pi, integral a to b, e to power minus all right. So how much is this? Now note that when this combines with this, this becomes 1 . So you can show that this quantity, this root m goes over here, and what does this quantity becomes to be? So this is root m or root 2 pi into root m multiplied by this minus this. So this becomes 1 . And then 1 minus 1 will get cancelled with this, and you are left with sigma naught square by nm. By n by sigma naught square plus 1 by m. Is that okay? And now this root m will become root m, and that would go to 0, this would go to 0, and then this quantity integral a to b e power minus x square by 2m dx. Now note that as m goes to infinity, this quantity will go to 0, so this will go to b minus a. B minus a, even if it is infinite, 1 upon infinite will go to 0. Root m with multiplied by with this will go to 0, because there will still be a root m over here. So that goes to 0. As m goes to infinity, this goes to a finite quantity. So everything goes to 0. And that proves that x bar is at misspin. Minimaxity of x bar would follow using a result which we'll do later on. So these were some of the problems dealing with assignment number 4. So let me stop over here. If the need be, we'll discuss some more problems in the next problem solving session. Thank you very much.